Hello students, welcome back. Let's go back to section 3, and this time let's try to complete it, I hope. Okay, alright. Previously we studied the general solution theorem. Let's suppose we have a homogeneous linear ODE like this. Then there are n linearly independent solutions, y1 through yn. So we have the linear independence. That's done. Actually we did it earlier as well, but I left a lot of holes and jumped over because I wasn't really requiring linear algebra to general public. But in this optional video, I went really thoroughly, spent double the time to explain this. Now, how about the second statement here? We are still not ready. Instead, we went through some of those preparations. Here's something obvious. If you have a set of solutions, then the linear combinations of any solutions is also a solution, like this. And this is just a trivial observation. It's basically a repetition of this same thing here, this one. The solution set of the homogeneous linear equation is a linear space or vector space, or in other words, closed on the linear combination. That's basically what this thing is all about, except that instead of having two functions, we are having m functions, but it's just a repetition. So the detail is left to the students. But in any case, what's the conclusion? The solution set of the homogeneous linear ODE is actually a solution space, a vector space. And then combine that with the first statement here, we have a linearly independent family of that vector space. And if you apply the second statement here as well, then the linearly independent family actually spans or generates the entire vector space as well. So y1 through yn is basis. Number of bases do not change, so the solution space has dimension n if the original linear ODE has order n. That's a big idea. So the dimension doesn't change. So if you use some other methods to find n linearly independent solutions, that's a basis too. And it can generate the entire solution space. So any solution y can be written as a linear combination of those n basis vectors too. Here, vector I mean by functions. But then again, the second statement is a little bit harder. So we need some further preparation. This one was just trivial. And this one was more significant. What we want is this. Functions y1 through yn are linearly independent if and only if the vector functions, like these, the column vector functions, are linearly independent. The key lemma was this. The linear combination of the original functions y1 through yn are constantly equal to 0. Then the linear combination of these vector functions, the column vector functions, is constantly equal to 0. Those two are equivalent. And how did it prove it? The if part was just triviality, because the second statement here means it's true for all those lines, first line, second line, all those lines. But if you look at just first line, that's the same as the other statement. So the second statement is actually stronger. So that was just a trivial observation. The other direction was a bit of a challenge. If this is true, then first line is true. How about the other lines? We simply take the derivative. First derivative, then we get the second. We get second line. Second derivative, we get the third line. Third derivative, we get the fourth line, and so on. And n minus first derivative, we have the last line, nth line. So we have all that. And then apply all these to linear independence. Then you get the desired conclusion. So this pink part and that pink part are equivalent. So replace them. Then we have the equivalent statement. So what's the conclusion here? y1 through yn are linearly independent. Means these column vectors are linearly independent. Or vice versa. If these are linearly dependent, then these column vectors are linearly dependent. Where do we use these column vectors? We use them in
something called Wronskian determinant. Same vector here, column vector, first, second, and so on the end. And then what's the size of this matrix? There are n vectors, so there are n columns, and there are n minus 1 derivatives and plus the original, the zeroth derivative. So again, we have n rows. So this is a square matrix, so we can define determinant. And the determinant is 0 if and only if those column vectors are linearly dependent. Remember, all those from linear algebra. So when we have linearly dependent solutions, then determinant has to be constantly equal to 0, because you see here, you're dealing with functions. So 0 vector there is actually a 0 function. So constantly 0, yes. For all t equal to 0, so constantly equal to 0. Proof is just that observation, nothing more than that. Linearly dependent means there exists a certain C1 through Cn, which are not all of them 0, some of them may be non-zero, yet the linear combination is equal to 0. Originally we have, of course, C1, Y1 plus C2, Y2, and so on. For all t. But then again, this is equivalent to this expression here with these column vector functions. So that's true for all t. Therefore, for all t, determinant is 0. So determinant is constantly 0. We get that. So that was just his trivial observation. Did I say trivial? Excuse me. It's not trivial. Still, straightforward observation coming from linear algebra. The other one, on the other hand, is in completely different dimension. Now, non-zero is one thing. Never zero is quite another. Constantly 0, so otherwise you have to have non-zero, which means you may have some non-zero value, but we may have some 0 values as well. For example, if a function cuts through the x-axis several times, then you get some zeros there, and then mostly non-zero. What this theorem says is that cannot happen. Wronskian is never 0, and that's different. Constantly 0, okay, from the idea of this linear dependence, and also from the linear dependence and the determinant. Yes, we get constantly 0. Yes, that's coming from linear algebra. But never 0, that's a different story. So let's prove that. Okay. Ready? Okay, let y1 through yn be solutions of homogeneous equation, alright? And if they are linearly independent solutions, then determinant is never 0, which means non-zero for every t. Before starting the proof, let me emphasize the difficulty yet once more time. I already said it many times, but let me emphasize it yet once again. Here for linearly dependent case, identically 0, always 0. So if you simply take the negation, then it simply says non-zero. So it can be non-zero for some t value, but it could have been zeros as well. What this theorem says is something a lot stronger, never 0. So that's what we have to prove. Okay, here we go. It's hard. And also, before starting, let me have a reminder here. The fundamental theorem of linear algebra, the fundamental theorem of linear ODEs. A linear ODE has a unique solution under a given initial condition. More precisely speaking, we need interval of definition. So inside that interval of definition, under a appropriate initial condition, we have to have a unique solution, one and only solution, always. All right, let's begin. Let y1 through yn be linearly independent solutions, yet there is a t0 such that determinant is 0. Yes, yeah. Let's assume determinant can be 0. So basically we want to drive some contradiction here. We want to prove that determinant is never 0, so we assume it is 0 for some t0. Its difference same always 0. It could be non-zero for some other t value, but for some t0, let's assume determinant is 0. And of course, what we want is a contradiction. Now, for this t0 value, we're going to get numbers here. y1 of t0, y1 prime of t0, all these are numbers. If you get just t's, all these columns, those are functions. Column vector functions. But here, these are numbers. And all these numbers, so we have these n vectors in Rn, and they are linearly dependent. So they are linearly dependent, so we can find an n-tuple of numbers C1, C2, C3, and so on, which are not all 0, some of them non-zero, so that the linear combination is 0. You can do it like that. Now here's a clever idea. Without loss of generality, we can assume C1 is non-zero. Well, what if C1 is 0? Well, there got to be some non-zero somewhere. For example, C17 is non-zero. Switch it around and rename it. And I can make C1 is non-zero. It's just switching the order, and addition is commutative. You can always do that. That's basically what we say by what you mean by this without loss of generality. So without loss of generality, C1 is non-zero, so we can divide by C1. Here we go, divide by C1. Maybe it was a bit premature. From here, divide by C1, and then solve for this column vector here. And this is what we get. Negative C2 over C1 times this, plus negative C3 over C1 times the next column vector, and so on. C1s are in denominator, and it's okay. All right, these are for t0s. But what we want is for other t values as well. So we're going to define a new function y star like this. Now this is true for all t. True for t0 as well, but all t, because that's the definition. We are defining a new function like this. And of course, at t0 we have that. Now what is this y star? Is it different from y1? It'll turn out to be the same, and that's what we want to prove. You see, for y1, we know this. We proved it thus far. But for other t values, do we have the same linear combination? We don't know that. But we want to prove it. So how do we do that? We introduce another function as a linear combination, y star. And we want to prove that y star is same as y1. Consequently, y1 satisfies the same linear combination like this for other t values as well. Tricky, tricky, tricky. Now, y star is a linear combination of y2 through yn, so it's a solution of the original homogeneous ODE. And y star and y1 share the same initial condition. All these values are the same. Because right-hand side is the same. So at t0, these two are the same. So what conclusion do I draw? They share the same initial condition, and they're both solutions. And solution is unique for all linear ODEs within the interval of definition for given identical initial condition. So these two must be the same. Y star and y1 are the same. Therefore, what did it say about y star? Y star is defined as a linear combination like this, and y star and y1 are the same. Then y1 can be written as this exactly the same linear combination now. So y1 is a linear combination of y2 through yn. So that's what we got. And that's a contradiction because y1 through yn are now linearly dependent. That's a contradiction. We assumed they were linearly independent, but with all those analyses using the fundamental theorem, by introducing y star, we got linear dependence. There goes the contradiction. Where did all the contradiction come into play? We made this bad assumption. Let's suppose there is a certain t0 so that the determinant is 0. Otherwise, we just use all those logic, rigorous logic. So that's got to be false. So such t0 does not exist. So determinant becomes 0 for no such t0. In other words, it's always non-zero. So there goes the proof. The Wronskian determinant is either identically 0 for linearly dependent case or never 0 for linearly independent case. Okay, will that help us proving the conclusion of this general solution theorem? Okay, let's try. So let's suppose we have a solution L of y equal to 0, and we want to prove that y can be written as a linear combination of y1, y2, y3, and so on. Okay, all right. Let y be a solution and take all those together. Y and then y1, y2, y3, all the way over to yn. What if they are linearly dependent? And then what if they are linearly independent? Let's consider linearly dependent case first, and that's the case we want actually. If they are linearly dependent, then it is possible to find coefficients b0, b1, b2, and so on, so that the linear combination is identically 0. Yes, that's a definition of linear dependence. But then again, please make this observation. b0 cannot be 0. If b0 is 0, then this entire part drops out. And then we have a linear combination of y1 through yn. And thus, all these coefficients must be 0 because y1 through yn are linearly independent. So we have all 0. So b0 cannot be 0, so b0 is always non-zero, which means I can divide by b0. So from here, I can divide by b0 and then solve for y of t. So divide by b0, divide by b0, I can always do that. And then flip all those things to the other side, and what we have the desired linear combination. Y can be written as a linear combination of the others. That's precisely what we wanted. So if they are linearly dependent, all good. What if they are linearly independent? We're going to prove that it's impossible. If they're linearly independent, then these column vectors are linearly independent. We went through that in the previous lemma. And therefore, the determinant is never 0. But then again, this is impossible because the rows are linearly dependent. You see, columns are linearly independent. That was my assumption. But what if I change the viewpoint and look at the rows? Rows are linearly dependent. If I select this coefficient as the A1, A2, A0, A1, A2, and so on, which originally came from this original linear ODE, like this, then take each component. That each component is the left-hand side of the original linear ODE. And all these y, y1, y2, those are solutions. So you have to have zeros. So what do you have? This linear combination is a 0 vector constantly for all t. So the rows are linearly dependent, therefore determinant should be 0. So there goes contradiction. They're not linearly dependent, that's impossible. They're always linearly dependent, in which case you can solve for y and you're going to get the linear combination expression. And that's precisely what we wanted to prove, and we got it done.